So we are Ruxandra and Gabriela, and we work with white dwarfs. Ruxandra works with white dwarf populations, and myself, I'm working with white dwarf interactions. So first of all, you need to know what a white dwarf is. A white dwarf is the final evolutionary state of most of the stars. So the fate of a star is determined by its mass. The most massive stars are going to explode most of the times and to leave a remnant which is going to be either a black hole or a neutron star. Whilst the stars that are similar to our sun, or up to 8 times as massive as the sun, they are going to become a red giant, and then at some point they are going to expel the outer layers and to form a planetary nebula and a white dwarf. So white dwarfs are very common. More than 98% of the stars are going to end up as white dwarfs. And they are also very interesting because they can lead to phenomena as supernova type 1a, which are very important because they have been used as cosmological tools, for example, to determine that the universe was expanding. But, however, despite the importance of these explosions, the progenitor systems are still uncertain of these explosions. So that's what we have. We have white dwarfs. Since they come from stellar cores, they are very dense. This means that they are as massive as the sun and as small as the Earth. So the physics that are working here are different. For example, when a white dwarf loses mass, it gets bigger, and when it gains, it gets smaller. And this property, it's interesting because it can lead to violent runaways. And that's what we are interested in. So another thing that you should know is that half of the stars don't live alone. They live in binary, triple, or multistellar systems. And at some point, because of physical mechanisms, they can start to interact with each other. And then a collision or a merger might happen. So that's what we simulate, these interactions, which can be collisions or mergers. And as you can see at the left side, well, you cannot see it very well, but a large amount of nickel was synthesized in this collision. And this is an indicator that a type 1a supernova might have happened here. So that's what we are doing, simulating white dwarfs, mergers, and collisions. And the question is, how do we do this? So the technique that we use is called smoothed particle hydrodynamics. This is a numerical tool. And well, what you have to do is to simulate the plasma of the stars. No? So you are simulating a fluid. And what it does, this method, is to discretize the fluid into particles. And each particle has its own properties, as density, temperature, pressure, composition, or whatever you want. And the properties of these particles come determined by the interactions of the neighboring particles, in such a way that the closest particles influence more than the farther particles. And these interactions is also smooth using a function called kernel, so that the properties come integrated through this kernel. So with this method and adding the physics that you need, as in our case, nuclear reactions, gravitational interaction, equations of state, adding all this physics into this method, you can solve the equation that model your fluid and obtain reliable simulations as the one that we are doing.
Okay, I hope you hear me okay. As Gabriela said, I study white dwarf populations, and to do this, I use Monte Carlo methods. What are Monte Carlo methods? Basically, they're any type of computational algorithm that use repeated random sampling. Repeated random sampling is something quite easy. Imagine you have an interval, and you want to pick random numbers out of that interval. But you also have a probability distribution function, which means that although the numbers will be random, you will pick more out of that region where the probability is higher and less out of that region where the probability is lower. Now, this idea arose during the conception of the Manhattan Project, which led to the first atomic bombs, where two scientists were studying radiation shielding, which proved rather complicated for conventional mathematics. So one of them had the idea to do it like a solitaire game. So you just deal the cards over and over and over, and in the end, you compute how many games you won. And they named it Monte Carlo because actually one of them had an uncle which did his gambling at this casino. Now, how do I use this? Basically, I need a population, so I need a lot of stars. And for every star, I need some characteristics, like mass, time of birth, position, velocity. So I just random sample at the beginning for every star these characteristics using some distribution functions from other authors. And I obtained something like this, for example, the blue circles. It is important to say that I need to be able to compare my population with real observations. So I have to respect some conditions and some restrictions. But what do I do now? I have the stars, I have their initial characteristics, and I evolve them up to a desired age. Then I extract some astrophysical magnitudes, which are the same that an observational scientist can measure. In the end, I decide which of the stars have become white dwarfs, and I have a sample, and I do this over and over again until I have a large number of samples, and I can average out what is called the white dwarf luminosity function. This, in fact, is another distribution function which basically counts white dwarfs according to their luminosity. So, why do we do this? Well, this function is very interesting because it has that abrupt cutoff at the end, which tells us that the population's age is finite. And if we manage to match our synthetic luminosity function with an observational one, then we can deduce important characteristics of the real population, for example, its age, or we can see how certain parameters like metallicity and others affect the population. And this in the literature is known as white dwarf cosmochronography. And more or less it's what I do up to now. Now, besides astrophysics, the computational methods that we use are interesting for other fields. For example, what Gabriela does, SPH, can be used largely in fluid simulations, and we have some nice examples of how it's used in movies to render water more realistically. Or it has also been used in mechanics to simulate various things like impact, fractures, fragmentations, and others. Monte Carlo has a very wide range of applications. It can be used in mathematics, it can be used in engineering for wind technology, it can be used in physics, in quantum physics for the n-body problem you saw before in the other presentation. Also, it can be used in computer graphics for 3D rendering, in genetics, and many more. So besides learning a little about white dwarfs, I hope these computational methods can seem interesting for your field, and I thank you for your attention.